morning. Hello.
Hello, good morning, Veronica.
¿Cómo estás? Espero que tengas un café.
Sí, tengo.
Muy bien.
¿Tú?
Vale.
¿Todo bien?
Todo bien, sí. Maybe I start sharing. Yes. Yeah, it is. Okay, cool. So this is how many people share or sign up for this school, Luca?
Yesterday there were 100 participants between the Zoom and the YouTube channel.
And I guess it's people mostly from the nodes of Invisibles or Hidden, no?
So actually, I just saw the names of these participants. There are many from Asia. A very good part from Europe. America, it would be
difficult.
So, but we got some messages that they will attend offline. So looking at the video that are in YouTube. So in principle, there are more than 100 participants at the end.
That's good. But it's really international, eh?
We're happy that this is in this way. We managed to reach a lot of people, yes. So let me... Oh,
I'm going to write some references.
Okay, Veronica, there's already a message from one of the students who's asking to explain again the Lie group parameters.
Okay. That's fine. Yeah, we are going to start today with the Lie groups, no problem.
Very good.
And just writing down some references for the students to look at other books and so on.
Very good.
If they can understand my writing, of course.
It's very clear, don't worry.
Aspects of symmetry.
Okay, whenever you are ready, we can start.
I don't know if to put the camera. I don't think anyone cares about my face, but let's see. That's the camera. Fantastic. Okay, and now to this. Perfect.
So everybody, good morning, everybody. This is the second lecture of this Invisible School 2021. And yeah, let's continue with the standard model next lecture by Veronica Sanz from Valencia. And here you go. Please, Veronica.
Hi, good morning. Okay, so you survived yesterday class, that's good. We are going to continue in our path towards understanding the symmetry principles that are behind the standard model success, with the idea that, of course, you understand better the standard model structure, but also that helps you build new models for new physics, because you are in a school of, mostly BSM people, right, beyond the standard model. Just wanted to give you some references in case you want to read more. In terms of the Lie groups, Lie algebras, and so on, I think the best book is the one of Howard Georgi. That's called Lie Algebras in Particle Physics. In terms of concepts related to the structure, the symmetry structure of the standard model, I think this book of Pierre Ramon is really, really good, Field Theory, a Modern Primer. Then there is a book that I really love that is made up of some lectures that Sidney Coleman gave in a school somewhere, and it's called Aspects of Symmetry. It's nice, this book. It has aged a tiny bit because many years ago, the main subjects, the people were worried about different things that they are worried nowadays. But I think when it comes to understanding the deeper structure of electroweak symmetry breaking. This book by Sidney Coleman is, I think, great. And then there is this whole set of books by Landau and Lifshitz. Lifshitz, let me write it properly. Lifshitz. That is called field theory or classical field theory, théorie des champs, depends on what language you read it. This book, I think, is really good. It's fantastic. It's written by Russian scientists, and what it means is that sometimes they make, leaps of understanding. They tend to be sometimes a bit cryptic, but when it comes to this issue related to, yesterday I was telling you how everything comes from an action, and imposing symmetries on that action is what leads to, for example, obtaining, special relativity, electromagnetism, as you learned it in the undergrad courses. I think the best description of that, how the Landau and Lifshitz, they start by saying, let's write an action that satisfies a set of symmetries, symmetry principles, and some physical conditions. And then they come out with the special relativity, they come out with electromagnetism, and they do everything very, very explicitly. So you want to understand this a bit more, it's like kind of relearning what you already know. So many years of electromagnetism, and it just, the Landau and Lifshitz just do it in like one chapter, like this, starting from a very simple action. So at least you connect the kind of things you learn, the objects you learn from quantum field theory, let's say this F mu nu, and why they are actually the objects that you need to deal with when you want to write something that is consistent with the symmetries of space-time and the U1 symmetry, okay? So I just wanted to give you references. The other thing I want to do is to answer a question by one of the students yesterday. One of the students said that they have been working in dark matter physics, building models for dark matter or studying the properties of dark matter. And I assume many of you guys are studying this or working on this. So I thought it would be interesting to answer that question to everyone. So what he was asking, or she actually, it's difficult, I never know the gender of people, doesn't matter. What they were asking is that whether this discussion about Z3 that I gave and these different representations and so on, this will be something that could be applied to dark matter, because they are used to think about Z2 as a way or as a property of dark matter. So I want to spend like a few minutes talking about this. It's probably quite relevant to many of you. So first of all, what is dark matter? You know that dark matter is possibly a massive, electromagnetically neutral. It probably doesn't have an electromagnetic charge, otherwise we would have seen it, and it's dark, so it's probably doesn't have a charge, and it's likely to be stable, at least at some point, because we know that structure formation and so on, and the properties of dark matter are consistent with dark matter as being a heavy particle that it was around us a long time ago and is still around us, right? So it's this issue in dark matter that we are dealing with a massive particle that is stable. Whereas, assuming that a new particle doesn't have electromagnetic charge, it's not that hard, you say, okay, doesn't have electromagnetic charge, fine. And that is massive, it's not that hard either, because if it comes from a new sector, you can give it a mass, impose a mass in the Lagrangian, or say that it acquires a mass through some other sector, some other breaking somewhere else. The linking the massiveness of dark matter to stability, that's a problem. That's typically a problem. So I want to explain why. This is also the case in the standard model. In the standard model, when we write, we have all these particles, leptons, quarks, gauge bosons, and so on. Most of these particles are unstable. They don't live forever. And in fact, if you look at this at the fermion sector, you know that only the electron and a particular combination of quarks, which makes up the proton, are stable, okay? The reason is that kinematically, if you have a particle that is massive, and there are other particles around that are less massive, it will find a way to decay into these lighter particles, okay? And it will find a way, and it doesn't matter how long does it take and so on, even if it's at 20 loops, if it's possible to decay, it will decay. It will take time or it will be difficult, but it will decay. So in the standard model, there are interactions that are shared by many particles. So a muon can decay to electrons, a neutron can decay to protons, electrons, and so on. For example, the neutron, we know, decays to a proton and an electron and a neutrino, like in about 15 minutes. The reason is that the neutron is heavier than the proton, the electron, and the neutrino, so it can decay kinematically, that's allowed. So coming back to dark matter, this possible new sector, we have a massive particle, so it's heavy, yet it has to be stable. Something needs to ensure that it's stable. There are no order in perturbation theory or in non-perturbative phenomena. This dark matter should not decay. And the simplest way to ensure that is actually to copy the standard model. What's happening in the standard model? In the standard model, the electron is very light, okay? It has electric charge. It has something that we call lepton number. So it's the lightest particle with those properties. So for the electron to decay into anything, it should decay into something lighter and still preserve those properties. So it should decay into something with lepton number and charge and still being lighter. And since there is nothing lighter than the electron that has lepton number and the charge combination of the electron, this decay is forbidden by symmetries. What happens with the proton? Exactly the same. The proton is the lightest particle with a conserved quantum number, which is baryon number. So in order to decay to something else, it should be able to find another particle with baryon number that is lighter than the proton. And there is none in nature, so this is forbidden. Baryon number and electric charge, okay? And that makes the electron and the proton stable in standard model. Whereas the neutron happily can decay into a proton because the baryon number in that decay will be conserved. You go from one baryon number to another, the same baryon number in the proton. And here, this electron and neutrino have the opposite lepton number. And then the electric charge is adjusted thanks to the opposite charges of protons and electrons, okay? So for dark matter, we do exactly the same. We try to find or charge the dark matter under a conserved quantum number and to make that dark matter to be the lightest particle that has that quantum number. So no matter how massive it is, if it's the lightest particle with that quantum number, it will have nothing to decay to. So yesterday we were talking about Z3, and I told you that a possible representation of Z3 was precisely this root cubic, of solutions, which could be represented in many ways, but one possible way it could be represented is in the complex plane, where we put the real and the imaginary, and these three solutions of this equation will be one, exponential of I 2 pi over 3, and exponential of I 4 pi over 3. Those are the three possible solutions, and anything else is just a rotation of that, okay? So In dark matter, the usual Z2, the situation is very similar, except that now the Z2 can be represented as these two solutions, -1 to 1. Okay, so in the usual dark matter Z2 construction, it's simply the simplest idea. What you are going to do is to say that there is a Z2 symmetry in nature that is preserved, that you want to preserve. That means that the Lagrangian or the action have to preserve that symmetry. And what it means is that under Z2 transformations, the Lagrangian should not transform. That means that the Lagrangian preserves that symmetry. Sometimes we also say that the Lagrangian, that object, has to be a singlet under the Z2. Now, what is a Lagrangian made of? If you want to describe the standard model, you already know the Lagrangian. If you want to describe dark matter, let's say that is scalar dark matter, fermion dark matter, you know that you should write a kinetic term that allows dark matter to be able to propagate and to be a physical degree of freedom, and you will need some kind of mass to describe its massiveness, and you will also need some kind of interactions that can describe the decay or not of dark matter, the annihilation of dark matter, and so on. So the idea of making dark matter stable is to charge it under Z2, so that this dark matter is not a singlet. What you do then is the following. You say, okay, so I'm going to think of a new sector of physics where under a new symmetry, Z2, and under this symmetry, a standard model particle, a field, electron, proton, tau, whatever, and this Z2 transformation is going to do nothing. Okay, it's going to stay the same. It's a singlet under Z2. It doesn't feel that symmetry. And what it means is that it's in here. It's in this representation. But I'm going to have another sector. Let me call it the dark matter sector that under Z2 transformations is going to change sign. And what it means is in this area, is this in this type of representation. Okay, that's the way it does transform. What is the impact of imposing this? Is that since I know my Lagrangian, my action preserves Z2, this is what I'm assuming, then of course I can write things that are quadratic in dark matter. So anything, a kinetic term or a mass term, they will be quadratic on dark matter fields. That is a singlet under Z2. But I cannot write any kind of interaction that is linear on dark matter. So anything that is dark matter and a number of standard model fields, any kind of interaction of that type is going to change sign. Okay? Fine, so means that these kind of interactions are forbidden by the Z2 symmetry. And what it means then is that if I try to write dark matter that decays into any number of lighter standard model particles, that diagram is forbidden by the Z2 symmetry. Now, this doesn't mean that dark matter does not interact with the standard model, because I can always write an annihilation diagram that, for example, contains two dark matters and a number of standard model particles. So the dark matter, in that case, is stable because the decay process is forbidden, but it can annihilate and interact and do lots of interesting stuff in the early universe with standard model particles. Okay? Fine, so coming back to the Z3, this is the typical scenario, it's the simplest, it's very much copying what happens in In the standard model, there is a conserved quantum number. The lightest particle with that quantum number, no matter how heavy it is going to be stable. And this is the kind of procedure that you use, for example, in supersymmetry. In supersymmetry, you assume there is a kind of Z2 symmetry that is called R parity, and the lightest R symmetric particle is going to be stable. Or in extra dimensions, you could think on a Kaluza-Klein symmetry that will also ensure stability. But typically in dark matter models, you will just say there is a Z2. This Z2 might come from the breaking of a larger symmetry group, but at low energies, I just have a simple parity. This is often called just parity of Z2 because it's simply a sign. It's either +1 or -1. So coming back to the question of the student, yes, Z3 can be used exactly the same to ensure the stability of dark matter. The only difference respect to Z2 is also you can still use that Z3 symmetry. You will ensure the stability of the dark matter, but now the interactions will be slightly different because now instead of having with Z2, you can have dark matter square times a standard model. With Z3, you will need quadratic terms that are dark matter complex conjugate dark matter. So you can build masses and kinetic terms, but interactions, they will typically be with 3 dark matter particles and some number of standard model particles. So the annihilation, the history of dark matter, it will change depending on whether it's Z2, Z3, or any Zn that you're using. Okay, so yeah, there are differences, and you can use these symmetries to ensure the stability of dark matter. And this is typically what you would do. Make sure that your dark matter is stable through some simple parity or something more complicated. Okay, so now I'm going to move back to the issue we were discussing yesterday. Among all the symmetries, symmetry groups and so on that we want to consider in physics, the ones that are very, very useful and that help us understanding the deeper structure of the standard model are actually symmetries that have some level of locality. And then we enter into this area of Lie groups and Lie algebra. So groups, in this case, is groups of symmetries. So remember that a symmetry mathematically is represented as a group. So this just means symmetry, a representation of symmetry. And Lie here just means that it has some local structure. And I was telling you yesterday that you want to think on these group elements as depending on some kind of parameter that you want to be able to vary and actually expand near alpha going to 0. And what you are going to care about is mostly this local structure, some kind of infinitesimal structure close to alpha equals 0. Okay. This is a group element. This is an infinitesimal structure of your group element. So really close to alpha equals 0, really close to just unity, which means no symmetry transformation. And what you want to evaluate is how, as you move a bit further from no symmetry transformation, so you move a bit further from alpha equals 0, what kind of behavior your objects have, your symmetry has. I told you that typically you will actually exponentiate this, so keep this notation where the first derivative that is represented by TA is there, and just represent this in an exponential form where you will do that kind of representation of your symmetry transformation. These two, of course, at linear order agree with each other. Okay, so this is usually called a finite transformation. This is usually called a generator of the symmetry transformation. And what I was telling you yesterday is that you can deal with the symmetry groups, the Lie groups, directly. The exponential form, the finite transformation, that form is usually quite convenient because you know that whenever you exponentiate something, then combinations of different transformation properties become interesting or easy to deal with. Because think that what we are trying to do is we have objects and we want to apply symmetry transformations to them and see how they then transform, no? And examine these kind of transformations to try to build objects, in this case Lagrangian actions, that are invariant under these symmetries. So to have an exponential form for the symmetry transformation is useful because you might want to do a symmetry transformation and then do another one on top. And then you might want to actually see what happens if you first do one and then the other, or vice versa. You want to see how this symmetry actually behaves when you combine several of them. Okay? But since we are dealing with physics, and physics tends to be local, then we actually don't care so much about finite transformations in general. The deeper structure, the more abstract structure of symmetries is actually obtained when we look closely at alpha equals 0, when we look at the generators and we look how, as we move a tiny bit from alpha equals 0, how it behaves. So at the end of the day, we actually care mostly about generators, and these generators, TA, we care about their properties as they combine with each other, as they interact with each other. And the way they combine is usually through stuff like, in this case, a commutator. So to understand the symmetry behavior of a group, we might deal directly with the symmetry elements, these transformations, and we usually do it as a finite transformation in an exponential form. But more often, we care about the infinitesimal behavior of these Lie groups. And in particular, we care about something that is called the Lie algebra, which is take these generators, look at their commutator, and that commutator, that behavior is going to determine the symmetry properties of that group. Okay? So the Lie group, as you know, is a group, so it contains a lot of conditions, like for example, if I combine two elements of that group, I need to still have or produce an element inside that group. So closeness, associativity, and so on and so forth. So what it means for this Lie algebra and for the generators that come from a Lie group is that this commutator has to be proportional. When you take that commutator, you have to end up with another generator of that group. Let me call that another generator TC. Okay? So the only thing I need to do, if I want to understand from a Lie group the Lie algebra of that group, is to take these generators and take commutators and evaluate how, as I take A and B, whatever, so A and B fixed, what kind of linear combination with the other generators I get. Okay, and then I also then put an I in front because I love I's. No, it's because it's convenient. And I call those numbers here that I will evaluate the structure constants. So for any value of A and B, so let's say 1, 2, what kind of linear combination I get in terms of the generators. Okay, so these structure constants are going to play an important role in thinking about symmetries and the way to introduce forces, interactions in nature as local symmetries, as Lie groups and Lie algebras. Okay, so again, because these F's here, these structure constants, come from a commutator, they are going to have very specific properties. For example, we know that FABC has to be antisymmetric under B and A, right? And we also know, because they are commutators, you can use the Hausdorff, whatever. In quantum mechanics, you probably learn how commutators commute with each other and so on. So these structure constants are also going to inherit, or you are going to be able to deduce some properties about the structure constants and combinations of those in the forms of that, using these Jacobi identities that you will use in quantum mechanics. It's not really important, all this. It's just math, and this is math that you can find in the Georgia book. But here the key physical intuition is that you want to describe symmetries, yes, as groups, as mathematical groups. And in physics, you are often considering particular types of groups which depend on a continuous parameter. Once you do that, you say, and by the way, I would like to examine the infinitesimal behavior of my symmetry transformations. And there is where we end up thinking about this Lie algebra. So we go from a Lie group structure to a Lie algebra, which is examining the same Lie group, but at an infinitesimal level. And this Lie algebra is summarized, if you want, as the structure constants. How these generators, if you want, interact with each other through their commutator. All right. I don't know if there are any questions. If not,
actually, yes, there is one. I was going to stop you.
Yes.
The question is, so are the structure constants always complex values since there is an I?
No, they don't have to be. They could be real as well. The structure constant precisely is the part of your commutator that is here. You already, by definition, put an I over there, just for convenience. There is nothing much there. No, but the structure constants can be real or complex. There is no condition over there.
Very good.
We are going to see examples anyway.
Okay, perfect. Thank you.
Okay, so fine. So I told you yesterday as well that you can define a symmetry like Z3, and you can find different representations of the same symmetry. And those representations will be more or less convenient depending on what kind of objects here you want to apply the symmetry to. So you have a fermion, a scalar, a gauge boson, I don't know, a position in a crystal. This object you want to apply a symmetry to is different. Hence, the representation of your symmetry has to adapt to whatever it has to talk to, right? So once we say the Lie algebra is that one, we are going to represent it that way. We are going to examine the properties of the Lie algebra through these commutators. To actually make any kind of progress or apply this to anything, we need to choose a representation. Okay, so the most common representation that you can use is what is called the adjoint representation. What is the idea is that you can have many types of TAs, of generators of a symmetry group, in many forms. They could be matrices, they could be faces, they could be whatever you want, as long as they have the same behavior in their commutator. It could be that the commutator is 0 and all the structure constants are 0. Or it could be that, it's something more complicated. So one possible choice, one choice that we could make for the representation of this TA is to make it as a matrix whose components, let me call them BC, are precisely the structure constants. So let me go slowly over this. We are going to evaluate a symmetry, how it behaves, how it acts over objects. And we want symmetries that can be examined at a differential level. So it's really like close to 1. So we consider then Lie groups. Then we realize that close to simply not symmetry, the behavior is determined by these generators. And yesterday I was telling you that these generators can be more than one because you have the different directions in which you can actually modify things. So if you thought about symmetries that are, let's say, of space-time, you could think on taking derivatives respect to x, y, z, respect to time, and so on. So these generators can be more than one. And that's why we have this label A. And now I'm telling you that a possible representations of this TA, where A can be 1, 2, 3, whatever number, is to build a matrix where the entries BC are precisely these structure constants. That is a choice. And that choice is called the adjoint representation of your symmetry group. Why is this relevant? Because this adjoint representation is of your Lie algebra is precisely what we use to represent forces in nature. In the standard model, our usual photon, Z, W, and gluon, when we write a Lagrangian involving photons, Z's, W's, gluons, and how they interact with anyone, their kinetic term, everything that we write about them, is in using this kind of representation. Okay? So when yesterday I was telling you how we like to say, oh, the standard model par, SU3, cross SU2, cross U1. This is code to say that the way we represent hypercharge is a U1 where the gauge boson, the force mediator of hypercharge, is under the adjoint representation of a group called U1. When we say SU2, same story. And we say SU3, when we talk about gluons, we say that there are the gluons, the way they behave and they interact, will be following the adjoint representation of SU3, another symmetry group. Okay? So what we are going to do next is to go into a specific group. For the moment, I'm talking very generically about Lie groups and Lie algebras. So now we are at least up to speed of the importance of understanding a Lie algebra. And we know that there is something that is called the adjoint representation that will be the key, our entry towards understanding interactions in the standard model, forces in nature. So let's do one example that is extremely useful and appears everywhere of one of these Lie groups, okay?
Veronica, before continuing, there's a question. Yeah. Is that always true in general? By exponentiating the generator of the Lie group, we will get the element of the Lie group?
Yes, this is usually the way you represent the elements of the Lie groups. So these TAs are the elements of the Lie algebra, and the Lie group is made up precisely exponentiating them. Okay, and this is just a parameter, it's a number if you want. Okay. And the things that do not change, the things that represent the symmetry are precisely these TAs.
Okay, very good.
Okay, so let's go into one example because I think that's going to help a lot. And it's an extremely useful example. It appears everywhere. You get sick of SU2. SU2 is a group. The letters are special, that's the S. Unitary, the U. Transformations of two parameters, 2. There are many ways of representing SU2. They are our key to understanding the properties or the W's and Z's and the photon, the electroweak sector, and the forces in the electroweak sector. SU2 is super important to understand fermions, the fermion structure of any fermion in nature. SU2 is also very important to understand as well the Higgs properties, the interactions between nucleons. It's also very important to understand lots of things related to global symmetries that then you will use for your, let's say, model building and so on. So it's one group, SU2, and there are many ways of using it and let's say, making use of these properties. So what is SU2? SU2 is, now we can define SU2 quite simply because SU2 is the group where when you take TA, TB, and you say, I'm going to put an I in front, I'm going to put a C here, and I'm going to evaluate the structure constants. It's the simplest choice you can make there. You could put the Levi-Civita of A, B, and C. So in a generic Lie algebra, this ABC, this FABC, the structure constants can be anything, can be numbers of any type. But what if we make the simplest choice of such an object is that our structure constants, FABC, happen to be the Levi-Civita symbol. I assume all of you know what Levi-Civita is, and if not, please Google, Wikipedia. Simply numbers, and they have a very simple set of properties that are precisely what we need for the structure constant. So that choice is SU2. That way it appears in so many places. It looks like when it comes to its structure, nature tends to be as simple as possible, and SU2 is like the simplest, non-trivial thing you could do, like simplest non-abelian, because this is non-abelian symmetry that you could imagine. Okay, so that's SU2. As long as you find a group of these matrices or a representation of TAs that satisfies that structure, you are actually dealing with a representation of SU2. What happens with the adjoint representation we just spoke about? So in the adjoint, what I'm saying is that the TAs are going to be the component BC is going to be simply the Levi-Civita ABC, right? With an I somewhere, and actually for convenience, people actually put a minus here. Doesn't matter, minus or an I is just a constant in front. This will not change the properties of your representation. Okay, so the adjoint representation in SU2 for that group is simply, for example, T3 is going to be I times 0, minus 1, 0, plus 1, and then zeros everywhere else. Now, the same happens with T2 and T1. You can write explicitly these entries. Now, notice that this T3 is exactly the same matrix that you will get if you did rotations along the z-axis So three-dimensional rotations, the usual, you take a point in 3 dimensions and you rotate it, but at an infinitesimal level. So let's say that I have a point over here and I want to rotate it around the z-axis, but I want to do just a tiny bit. So you will say that point then, here you don't do anything in the third component, and here you will have a simple rotation matrix of sinus, cosinus, sinus, cosinus, minus cosinus. It's simply two-dimensional rotations along the x, in the x and y components, preserving the z component. So this is not by chance. This SU2 is actually an infinitesimal representation of the usual rotations in 3D. I don't know how you were taught mechanics. I've always found super boring mechanics, but you were probably told about these Euler angles and how a finite rotation in 3D, any kind of generic rotation in 3 dimensions can be generated by these Euler angles. So it can be generated as 3 parameters, alpha, beta, and gamma, which will be actually given by these kind of transformations. Okay, so a generic rotation in 3 dimensions can be represented as some angles alpha, beta, and gamma that you are rotating along the axis that corresponds to T3, T1, and T2, where those are the SU2 components or representations in the adjoint. Okay, so there is a relation between the usual rotations in 3 dimensions and SU2. And that's indeed the case. With rotations in 3 dimensions are a set of transformations that are called special orthogonal transformations of 3-dimensional objects. So you take a point in 3 dimensions and you essentially multiply by a matrix that is orthogonal of 1. So that's orthogonal. And no determinant equals 1. Those are the ways you will rotate a point. And what we are saying is that there is a relation between SU2, the thing that is going to allow us to describe the properties of W's and Z bosons, or the Higgs and so on, and SO3, which are our usual 3-dimensional rotations. So the finite structure of this Lie group of symmetries, and this Lie group of symmetries is different, right? One is made of matrices that are orthogonal and special 3 dimensions and so on. This SU2 is made of different types of, it's a different type of group. But at the infinitesimal level, at the level of the Lie algebra now, so at the level of the generators, TA, the generators of SO3 and SU2 do agree with each other. They are actually the same. And that's what we call in group theory an isomorphism. Two groups that at final level, they look different. They are represented by different transformations, different matrices and so on. But at the infinitesimal level, they are actually the same because they are represented by the same Lie algebra. You will say, okay, and so what? What do I care? What we do care, because these kind of isomorphisms, this kind of intimate relations of two symmetry groups that they appear to be different, but at least locally they are the same, are very important. And for example, they will allow us to write a Lagrangian involving nucleons and involving pions, and through this isomorphism, we will be able to write consistent interactions between the pions and the nucleons in nuclear physics. Okay, so this isomorphism structure of symmetries is important. Okay, any questions? Otherwise, I continue.
There are no questions.
Cool, good, thanks. I continue like penciling down all these properties of SU2. There's a lot more that we can say about SU2. It's an extremely useful symmetry group. For example, let's go back to this SU2. We say that is represented by these matrices or this algebra, where if you take two generators, you actually get the Levi-Civita. And let me change notation just for aesthetics. Let me call this J. Like in quantum mechanics, you've been talking about angular momentum, right? And in quantum mechanics, at some point, they started talking about generalized angular momentum, and they told you that's the real space angular momentum plus the spin component, right? So this generalized angular momentum in quantum mechanics satisfies this particular property. So it is an SU2 representation as well. So anything that you learned in quantum mechanics that has to do with rotations, indeed in 3D, and also spin, and the possible relation between these two will come out thanks to these symmetry properties. Okay, so what is nice about thinking of a generalized angular momentum, but now from this point of view, is that we know that this is a statement about a symmetry, a Lie algebra, but we can choose any representation of this Lie algebra that satisfies those properties. So, for example, we can consider an n-dimensional representation of this JA, and depending on this n, this value of n, we can actually represent the properties of any type of spin particle. So for spin equals 0, or spin equals 1, or spin equals 1/2, or spin equals 2, or spin equals 3/2, if we want to represent the transformation properties of a spin 0, 1, 1/2, any of these guys, the only thing we need to do is to think of different dimensionalities of this representation. So the spin 0, as you know, are scalars. Their property is that they do not change. So it's not super interesting. A spin 1 is a vector. Is usually the way we represent forces. It's a spin 1 particle. A spin 1/2 is a fermion. A spin 2 is what we will call a graviton. And this is the type of object of representation that we will need to describe gravity interactions. And a spin 3/2 will be a Rarita, Schwinger type of particle, which is useful in, for example, nuclear physics, because they are spin 3/2 objects, but also if you do supersymmetry and supergravity, this is a possibility of a possible supersymmetric particle with a spin 3/2, okay? And you could also think on higher spins. The way we are going to write Lagrangians, kinetic terms, mass terms, interactions of these objects that are consistent with these symmetries is precisely choosing different representations of JA. If you want, is choosing matrices of a different dimensionality. In this case, is 2s plus 1, depending on the spin, that apply on objects that have that dimensionality. Okay? So for the case of a spin 0, is simply, there is nothing to say. For spin 1, you will need a larger matrix, spin 1/2, and so on and so forth. Okay? So you are already used to this because in quantum mechanics, you already dealt with spinors as a way of dealing with fermions. For example, you had talked about the electrons as having two components, one going up and one going down. And in this two component notation, you apply or angular momentum, generalized angular momentum was acting in a very specific way. So this action has to match whatever is the object is acting towards, right? So for spin 1/2, you will need a matrix of dimension 2 by 2. For spin 1, you will have another dimension, spin 2, and so on and so forth. But you see, all this is exactly the same JAs, the same Lie algebra, but simply different representations that are adapting to the object is going to talk to. Okay? So, what else?
May I make a couple of questions, Veronica?
Yeah, sure.
Is the right moment.
Sí.
The first question is, rotation matrix T3 is unique or can consider rotation in any direction? So this is probably referring to the matrix of T3 that you wrote in the previous slide.
Yeah. So T3, the same as when you learned about the spin, you remember that the third direction was kind of special, right? It's simply because in the third component, it's easier to represent as a physical thing that you can think of. So T3 is indeed an infinitesimal rotation along the z-axis. T1 and T2 don't have this simple representation. You don't say T1 is an infinitesimal under the x-axis or y-axis. And that's why I was telling you that it depends on how you've been taught mechanics and whether you have been taught about Euler angles. It's just it's a representation of a generic three-dimensional rotation. Along the z-axis is very simple, and on the x and y is a bit more complicated. So I will just direct the student to actually look at these Euler angles discussion. Any other question, Luca?
Yes, just one still connected with T3. What would be our guiding equation to determine T3, or so any of them?
So, I see. You see this equation here, right? So let's say that you take a representation of your matrices that is going to be 3 times 3. And you need to come out with 3 independent matrices that actually satisfy this condition over here. So one choice, I guess what I want to tell the student is that there is no unique choice. The same way that when you think about the presentations for the gluons, there is no unique choice. The simplest thing indeed is starting with this T that is going to be simply 0, 0 everywhere, minus 1, 1, and zeros, zeros in zeros. You start with something very, very simple that you can interpret. In your case, it's going to be an infinitesimal rotation under the third component. You call it T3 you want. You can call it anything you want, but let's say it's convenient for intuition. And from that, you have to come up with the other missing components, T1 and T2, taking this into account, these conditions. So in practice, the answer is there is no unique choice. There is a lot of physical intuition that goes into getting the right, let's say, answer. You could get different representations of your Lie algebra that are not so physically intuitive, and that will you want will not manifest so easily the relations, for example, between spin and angular momentum, or the different types of properties we want to describe.
And the last question, could you please again explain why the isomorphism of SU2 and SO3 has something to do with Lagrangian of nucleons and pions?
Yeah, so the answer is we are going to do that example in particular.
Very good.
Okay, yes, cool. If I get there.
Sure.
Cool. Then we talked about SU2, which is the first non-trivial example of a Lie algebra that already at that level is super useful because it starts, showing different properties. Like, for example, we can spin in nature, which we know is there and is an internal property of all fields and characterizes the way they behave. Spin is SU2. We know now that SU2 is actually related with another symmetry transformation, which is SO3, so rotations in 3 dimensions, space rotations, external rotations, at a level that is infinitesimal, so at the level of isomorphisms, and so on and so forth. So we see that SU2 is already playing an important role. But to make progress, to actually write Lagrangians that involve particles of different spin, we also have to take into account the properties of spacetime. So what I'm going to do is to move into a discussion of these properties of spacetime. Now, this is going to be, again, using symmetries. So we want to describe the action, the properties of nature through a Lagrangian, and we want to impose on that Lagrangian symmetries. And these symmetries can be external, so space-time symmetries. How do they behave, these fields, as we move from one place to another, as we rotate, as we boost, as we translate, and so on. And they will also be internal. And spin, baryon number, lepton number, all these things are internal properties. So we want to be able to account for both. And we need Lagrangians, we need actions that describe objects of different spins. So we need to understand SU2 in the context of actions that are invariant under some spacetime properties. Yesterday I was telling you that imposing symmetries of spacetime is what leads to the general relativity and special relativity. So it's not that special relativity appeared out of nowhere. For Einstein, of course, it came through some understanding of what nature should do, some principle. But actually, the real principle behind special relativity and general relativity is a different type, and it's a symmetry principle. Okay? So what we know, or we assume, if you want, is that nature at the level of space-time has to be Lorentz invariant. There is a symmetry that we believe is the correct symmetry for space and time. There is a group of transformations that I can do on the positions x mu, okay, whose properties, whose transformations preserve the space-time interval. Remember what was this space-time interval? This is, you can put it in differential form, it doesn't matter, is some metric eta mu, x mu, x nu. Okay? That quantity is the important quantity. So we think that nature, the way the properties of space-time of our fields and so on that we see, is actually a consequence of preservation of this space-time interval. The kind of group that will preserve this space-time interval is actually a group of transformations of x mu that is special orthogonal rotations but now 3 dimensions for space and 1 for time. This 3,1 is just to make the point that the behavior of space, 3-dimensional space and time is slightly different. There is, as you know, in this space-time interval, there will be a sign difference between space and time. Okay, so the whole special relativity, general relativity, and so on can be obtained by writing actions which are invariant under this particular set of transformations of the quadrivectors x mu. Okay. Again, a very good place to look at a discussion about this is precisely this Landau and Lifshitz classical field theory. So the type of transformations, matrices you want lambda, 4x4 transformations that preserve the space-time interval belong to a group of symmetry that is SO3, 1. Okay, so we can write this more explicitly, saying that those are transformations lambda that have to satisfy this property, where eta in this case is the geometry of your spacetime. Okay, so this SO3, 1 is the Lorentz group, but we know that there is the transformations we want to consider are both changing through Lorentz transformations. Here again, I'm making some assumptions about your education, and I assume most of you have been given a course on general relativity. But if not, I mean, fear not, it's not super important that you understand every detail over here. But if you have given GR or cosmology, you probably know what I'm talking about over here. But also, we want to be able to translate by a finite vector our original vector. Okay, so those are translations. So the kind of transformations of space-time that we want to consider are Lorentz transformations and also translations. And we want to see how under these transformations we can write actions that are invariant under this group. Now, a bit of just simply notation. Lorentz transformations, you know them, GR and so on. Translations, the sum of these two types of transformations are called Poincaré invariants on Poincaré transformations. It's simply notation. So Poincaré is the Lorentz of everyday, let's say, that you already heard about, and translations. Often when people talk about symmetries of space-time, they will say Lorentz because the translations are kind of obvious, let's say. But in fact, the symmetries of space-time we deal with are Poincaré, which are Lorentz plus translations, right? Okay.
Veronica, is lambda in the adjoint representation of SO31?
Yes.
That's it. Thank you.
Very good. So in general, a possible transformation that we can make on a vector or quadrivector will be a Lorentz matrix, something that acts on this x mu, and a possible vector A mu that translates it. One way of writing this, again, as a group in the exponential form is say, I'm going to represent this transformation as something, some parameter omega, where omega is simply a parameter, a number, with the generators of the Lorentz group. And we know that these generators have to be tensors, and some other parameter, in this case, A mu, with the generators of translations. So what I've done here is the following: is I'm talking about the symmetry group. And obviously, in the case of space-time symmetries, we want to think about the local properties. That's super clear, right? So we want to think about the symmetry group in general and a possible symmetry transformation, but we also want to think on the infinitesimal structure. What are the generators of the Lorentz and the translations? What are the generators of the Poincaré symmetry? And that's what we are going to discuss in a second. So we want to think on a possible generic Poincaré transformation as some parameter numbers times a generator of Lorentz, some parameter, again numbers, times the generator of translations. So let's go over this. These generators of the Lorentz group and the generators that correspond to the translations are operators. They act on states, and I'm going to, for simplicity and also because it's not terribly important again, I'm going to skip details that if you want to know more about, again, is in the literature I've given you. But you need to find a representation, an infinitesimal representation of the Poincaré group of symmetry. And you want to separate Lorentz and translations because they are in principle two different things. And you want to find also a representation of these infinitesimal generators in a way that connects to what you already learned from special relativity, from general relativity. So actually what happens is that you can write these generators of the Lorentz group as a combination of rotations and boosts. And again, here I'm assuming you had a course on special relativity, advanced course, and in general relativity, and you know what I'm talking about. And this generator of translations would be precisely the typical, momentum representation. It will end up being the momentum associated to a particle when we talk about a very simple situation. Okay. So think on these M's and P's and simply being some 4x4 matrices acting on 4 quadrivectors or vectors of 4 components. Then, if we want to understand the Lie algebra or the Poincaré group, what we need to understand is how these guys commute. So we want to know how these M's commute with each other, how the P's commute with each other, and how the N's and P's commute with each other. And what happens is...
Veronica said again, how could you guess that the generator of the Lorentz group has a second rank tensor?
What do you mean by guess? So you know that...
why it is a tensor, essentially.
It has to be a tensor, yeah. Exactly, because think that when you do a Lorentz transform, the M mu are infinitesimal transformations of this type, where x mu is going to go to this, right? So you do need some tensorial structure.
Yeah, I think that this sounds where the question.
Right, sounds good. Very good. So once you make this connection between what you already know, so that Lorentz transformations, the special relativity types of transformations that you will do in 4 dimensions, can be thought of as rotations in 3D and boosts. Remember that boost kind of mixes time and space. And rotations are simply 3-dimensional things of the, like the usual stuff you will do in mechanics. So you need to find a way of implementing inside this menu your rotations or identify inside your menu the rotations and boosts. And then the translations are simply, this, where it will end up being a momentum. So you do that, and what happens is that this commutator of P with P is 0. The subgroup of the Lie algebra of Poincaré, the subgroup that corresponds to translations, is actually an abelian subgroup. It commutes with itself. So acting, why is it abelian? Because if I have an object and I do PA, PB, so I actually translate by a value, a mu, and then another value, b mu, is the same as if I do the other way around. This is kind of obvious. I take a point and I change a value a, and then another value b, is the same if I did the opposite, okay? If I first started with one vector and another. So that this abelian part is kind of obvious. M with M leads back to another M. But when I commute M with P, I actually get back P. So just to not lose you, we are, as in the case of SU2 that we had done before, M mu nu. Before we were talking about TAs and we were talking about a matrix, no? Or a representation where this could be 1, 2, 3. Here we are actually talking about the same story where mu is 0, 1, 2, and 3. And here the same, we are talking about tensorial structure, but those tensors are made of matrices of a given representation of your symmetry. So from these matrices, you can go on and start asking, do these matrices do commute? And in the case of P, yes, they do commute. In the case of the M's and P's, they do not commute. They lead to another combination of M, and here another combination of P. Okay, so if we then explore this relation between M and the usual rotation generators and the boosts, so M can be written as some relation of rotations and boosts. Lorentz transformations are some combinations of rotations and boosts. That's what they are. Let me call the generators of rotation J, as that I've done before, and the ones of boost K, as you probably done in your courses. Okay, so when we do that, and we take this commutator, in terms of rotations and boosts, what we get is the following. We get that rotation with rotation leads to rotation. Boost with boost, when you look at this commutator, it leads to rotation. And boost with rotation goes back to boost. And in particular, it's not just proportional. It leads to I times, if I put the indices here, I times epsilon ijk, same here, I times epsilon ijk.
Veronica,
yeah.
all the screen disappeared. We are just seeing what you are writing right now.
Oh no, I pressed the button, damn it. Okay, good, thank you, Luca. Let me write it more properly. So this algebra of a menu of the Lorentz transformations can be written as algebra among the rotations and the boost. And this algebra is very simple. It says Ji, Jj is I times ijk, jk, ki boost with boost, exactly the same structure constants, exactly the same result, and then ki jj is I times ijk. K, K. Okay. So the Lorentz group, which we know is SO3, 1, right? When we look at the infinitesimal behavior of this Lorentz group, of this finite group, we see that is very similar to a bunch of something that looks like SU2s, right? This epsilon ijk is precisely the infinitesimal structure we expect from SU2. So it looks like there is a relation between SO3, 1, the symmetries of space-time, external symmetries, and SU2, which we know is what we use to represent, for example, spin. So what is going to happen is that when we want to write particles of spin, so in this representation of SU2, a particular representation of SU2, that are consistent with the symmetries of space-time, we are going to have to take into account this relation. We are going to use actually this similarity, this type of isomorphism between some SU2s and SO3, 1. Now, in order to do that, we need to clean up a tiny bit this stuff over here, because you see that it looks like the J's and K's, so the rotations and boosts kind of follow the algebra of SU2, except that it's kind of mixed, J's with J's lead to J's, but K's with K's lead to J's. So they are kind of mixed with each other. And same here. This mixed commutator is also leading to K. So the way it's written right now, although it's more intuitive because we are talking about rotations, we do have an intuition, and boosts, we do have an intuition, is not the most suitable way of thinking when we want to relate to SU2, so the physics of spin. So what we need to do is simply do a change of coordinates. What we do is to write what is called a complex Lie algebra, which is we are going to define S and A, new generators that are linear combinations of the original ones, of rotations and boosts. So there are of course indices. So instead of thinking of this algebra over here and how confusing it is, I'm going to rephrase it in terms of these linear combinations. Surprise, surprise, that's when we do it. When you do this, those properties end up being something much simpler. So it's S with S goes to S with the IJKs. I'm not going to write because I'm lazy. A with A leads to A, and A with A, S do not talk to each other. Okay. So now what we have gone through is we've written the Lorentz transformations. We've written in terms of a group. We looked at the algebra of that group, which means understanding its commutators. We've written these commutators in terms of things that are physically intuitive, which are rotations and boosts. And then we found that it's kind of smelling like SU2, but not yet there because it's kind of mixing with each other. We've rewritten these rotations and boosts in this particular way, two new linear combinations. And in terms of those S and A, we find that the real Lorentz structure, the intimate Lorentz structure at this Lie algebra level is one SU2 and another separate SU2. These S and these A's, each of them span the SU2 algebra, a different SU2. Okay, so what we learned is that yes, indeed, SO3, the Lorentz symmetry, the space-time symmetries, are related to the physics of spin, the SU2. But they are related to two separated SU2s, separated in the sense that their algebra does not talk to each other. So this is one type of physics, and this is one type of physics. So the real isomorphism between SO3, is actually with two SU2s, SU2 and another SU2, which we will denote because this is the traditional thing and it connects with the standard model lectures I'm giving you as left and right. Okay? So after massaging and playing with the Lie algebra of SO3, of space and symmetries, we realize that there is this isomorphic to two SU2s that do not talk to each other, that are in principle separated. And that will be our key to actually enter into spin and to understand how to describe spin particles in a way that is consistent with the space-time symmetries, Lorentz symmetries. So let's do that, okay?
Veronica, question.
Yeah.
What about the number of generators? I mean, SO3, 1, how many generators has? And SU2 cross U2, how many generators does it has?
Okay, very good. So we are talking about M mu. Then we talk about rotations and boosts. We just rephrase them in terms of rotations and boosts. And then we talk about S and A, right? Which were just linear combinations of J and K. So I'm not, if you want, I'm not doing anything there of introducing more or putting linear or putting less. S and A are simply linear combinations of the original generators. But there is a relation which is under parity. So it's a property that you could you might want to impose on your symmetry. Parity means x goes to minus x. Under parity, what is going to happen is that S goes to A. So when I say that SO3, 1 is isomorphic to SU2 left cross SU2 right, that anything I can write that is a space-time transformation, I can also write, so it's boosts or rotations, I can also write in terms of this new type of thinking, these two SU2s. These two can also be related using parity. But in terms of degrees of, not degrees of freedom, but it's simply S and A are simply linear combinations of the original generator. So there is no, you have introduced nothing new or nothing less.
Okay, this explains the question. Thank you.
Okay, very good. So whereas in SO3, 1, the generators are mu or boost and rotations, in here there will be two types of SU2s, S and A. That's it. All right, so now imagine then that we want to write a theory, a Lagrangian, that in that Lagrangian we want to impose both internal and external symmetries. We want to write a theory that is, for fermions that is consistent with the spin of these fermions and with the Lorentz properties of these fermions. I don't know how, like probably you've gone through this quantum mechanics, maybe you did quantum field theory, or some course in between like relativistic quantum mechanics, and you are told about this Dirac equation and so on, and you are told about spinors and I don't know if at some point you were thinking, why? This is so complicated, man. Why do we need all these things? Why the sigma Pauli matrices? Why all this? These things that were understood and written down by Fermi, Schwinger, and so on, they were actually necessary, this necessary consequence of trying to write both a theory that is consistent with a particle of definite spin and a theory that is Lorentz invariant. And although when you write a spinor, you know that there is a kind of vector in 2 dimensions or something, but you don't know these dimensions are some internal space of the spinorial space, and it all looks kind of very iffy, let's say, is actually the only way you can write things. And this is what we are going to do for the next 5 minutes or so, if Luca allows me.
Sure, please go on.
Thank you. So now, whenever I want to write a Lagrangian that is invariant under SO3, 1, I can then write a Lagrangian that in terms of the SU2 cross SU2 is under some representation of a spin n and a spin m, where this is the SU2 cross SU2. All right. So if we do this kind of parameterization, we can write objects that are 0, 0. So they do not transform under SU2. They do not have a spin. They are scalars. Or we can write something that is 1/2, 0, or 0, 1/2. What it means is that their properties are going to be carried over by 2-dimensional matrices of SU2 acting only on the first part, or 2-dimensional matrices of SU2 acting only on the second part of the second SU2. And this is called a left-handed spinor, and this is a right-handed spinor. Okay? So you could also think on this, looking at representations of 1/2, 1/2, and this representation is precisely what is called a Dirac fermion. Think that the kind of dimensions carried by these representations are matrices that are order 2s plus 1. So for scalars, it will be simply, just a function. For this, there will be a 2x2 matrix, the same for this, and this has to be 4x4 matrices, which are precisely the gamma matrices you use in your usual quantum field theory, whereas these 2x2 matrices are the Pauli matrices. So let me just I don't have a lot of time. I really want to move on into forces tomorrow. So tomorrow we will be talking about forces, how they are described, and so on. Fermions are tricky, and Rachel is going to give you the last day on Friday a tutorial on fermions. So I'm going to summarize very quickly how this fermionic structure that you learned by heart and that you were told this is the way to describe fermion, this is the way to describe a Majorana fermion, a Dirac fermion, and so on, is actually a consequence of these relations between SU2 and SU3, 1 of the Lorentz symmetry. And you usually talk about this 2-component spinor and or a Weil spinor. These are the left-handed or right-handed type of spinors. And this is the typical one that you will put, right? Spin up, spin down, that's it. And the way to think about the spin properties, you remember from quantum mechanics how you were using these Pauli matrices, which are precisely one representation, 2-dimensional representation of SU2 for S equals 1/2. Okay? But you've been also told about the 4-component Dirac spinors, where you essentially take a left-handed guy and right-handed guy and put it together. So why do we need to do this? I told you that this left-handed and right-handed SU2s are actually related by parity. So under parity, these SU2 left and right are related to each other. So you have interactions, you want to describe interactions of physics that is invariant under parity, for example, like electromagnetism. Right? In that case, if you write a Lagrangian with fermions that are only left-handed, that will violate parity. So you need to write a Lagrangian that involves left-handed fields and right-handed fields, and that they are related to each other in a very particular way. That's what the fact that electromagnetic interactions, that charged particles also have to preserve parity, is what forces the structure of Dirac spinors. What makes you to have to then consider gamma matrices that are 4x4 matrices involving combinations of these Pauli matrices that are 2x2 matrices. So it's not by chance, it's really a consequence of the symmetry of your interaction, that electromagnetism is a force, it's an interaction that involves particles and their internal structure, but also preserves some space-time properties, like, for example, parity. In that case, under parity, spinors are not, actors. They are not just witnesses. They actually care about parity. Parity changes left-handed spinors to right-handed Weyl spinors. So the only way to write a charged particle that is consistent with this kind of parity interactions is to combine it into a Dirac spinor. And then you have all these gamma matrices and so on that you had to deal with. So it's not by chance, it's really a consequence, a unique consequence of the symmetry properties that you want to describe. So let me just, all this, the Dirac equation, the Lagrangian for these particles, your Majorana particles, the way you write those spinors, that maybe for you, it was just a God-given, this is the way we write the spinors, and this is the way we write a kinetic term. It's actually the only way you can write a kinetic term for a Dirac spinor that is consistent, again, with Lorentz symmetry. Same for the mass terms, same for the interactions with gauge bosons, and so on. It's all a consequence of this SO3, 1, saying that your Lagrangian has to be invariant under SU3, 1, really determines the only types of terms you can write for your fermions. And I want to just quickly write it like a summary. Okay, so let's move to Dirac spinors, but you can do exactly the same with Weyl spinors. With Dirac spinors, the only way you can write a kinetic term that contains a derivative respect to mu. This is a 4-vector, right? So it has transformations under SO3, 1. So to combine my fermion properties and a derivative together, to make sure that I'm able to write a kinetic term, I really had to go through this structure that you already know, where you have psi bar, where psi bar has to do with complex conjugate emission, gamma 0, whatever, and I actually had to use this structure over here. So when you were told that the kinetic term for a fermion, the Dirac fermion, had this form, so the usual psi bar derivative psi, you might have thought that by just simply putting gamma mu and the mu stretched with each other, connected to each other, summing over these mu's, so you don't have any free Lorentz index, that was enough to produce something that is Lorentz invariant, but it's not. Because these guys do transform under Lorentz invariant and the Lorentz transformations. So the only way to make a kinetic term that is Lorentz invariant is actually having this particular gamma mu's with these particular properties and this particular guy over here, and so on and so forth. So there is a lot of symmetry. I mean, essentially the symmetry is telling you the only way you can write a kinetic term. And the same happens for mass terms. This side by side, that form is the only one that is invariant under this Lorentz symmetry for a Dirac fermion. But anyway, this is something that you will do with Rachel on Friday. Okay, so for Weyl fermions, for two-component spinors, for interactions that do not care about parity, for example, the electroweak interaction, breaks parity, then you can allow yourself a lot more things. So for neutrinos are not charged under electromagnetism, so they do not have to actually preserve parity. Their interactions do not preserve parity. So you can think of neutrinos as simple two-component spinors that have a left-handed or right-handed component only. You can write Lagrangians that do not have such very strong properties. And that's why for neutrinos, you are able often to write both a Dirac mass, so a mass of this type, and a Majorana mass. Okay, and again, is this additional freedom is thanks to the fact that the neutrinos do not have to preserve parity. Okay, and I think here I'm already stretched too much, but tomorrow what we are going to do is we are done with fermions. You will do a lot more with Rachel, hopefully, where she will explain about the Majorana masses and so on and so forth. If you work on neutrinos, you probably know that this is interesting and important. But tomorrow what we are going to do is talk about forces. And the last day we will talk about the Higgs mechanism. So that's the plan, okay?
Okay,
Thank you.
Thanks a lot, Veronica. Before leaving, there are 3 questions. So, is the relation SO31 approximate SU2 left, SU2 right, the reason why we call SO31 to be the double cover of SU2?
Yes.
Okay. The next question. The spinor 1/2 is a vector?
No. The spinor 1/2 is the Dirac fermion that has both left-handed and right-handed components. That we decide to, for convenience, represent it this way. But these are like 4 degrees of freedom, right? The one containing side left and inside right.
And
but it is...
you can finish if you want, if you were just commenting.
Just wanted to say that if you want to then describe a vector, you will need something that is a Lorentz vector, a simple, 4-component, right? Like this guy over here. And the gamma mu's are indeed a vector.
And the last question, about the Lorentz invariance of the Lagrangian. If the Lagrangian is not parity invariant, doesn't it break Lorentz invariance? For example, the electroweak theory?
No, exactly. That's a very good question. Yes, indeed. So this is an important point. We believe that Lorentz invariance is a fundamental symmetry of nature. And as a manifestation of this fundamental symmetry, we end up with general relativity, which we tested very well, special relativity when gravity is not so important, Newtonian mechanics when velocity is. So we think that this SO3,1 is actually determining the physics we do see. Now, there are indeed interactions that do not preserve parity. Electroweak interactions do not preserve parity. Okay, so what parity does is it relates SU2 left and right. Under parity, SU2 left is equals SU2 right. So left-handed and right-handed spinors should be, if you want, treated in exactly the same way. But yeah, indeed, electroweak interactions do not care about parity, so there you can write something that does have something that is purely left left-handed spinor or right-handed spinor. But many of the particles of the standard model, the ones we want to describe, the fermions we want to describe, are actually charged under electromagnetism, all the quarks and all the charged leptons. So for all these guys, we need to preserve parity. And the way to do that, the way to write a consistent theory, both with Lorentz invariance and that preserves parity, is actually using this Dirac-Spinor type of structure. But that's precisely what I was saying, that the only guys that do not care about this, they are not charged, they are neutrinos, and where you can actually play more games are the neutrinos, where instead of writing just Dirac structures, you could also write Majorana structures. So you could have different sources of masses. For Dirac, for charged particles, they need to have this kinetic term and this mass term, and nothing else is allowed. For neutrinos, you can do more stuff.
And in the third week of the school, we will see very, very deeply neutrinos. So
yeah, exactly. So
as well.
This is coming to you.
Thanks a lot. It has been fantastic. So I think we can close the second lecture if there are no other questions. Seems not. So thanks again, Veronica. And
see you tomorrow.